Okay, we're going to talk about section 5. We're in chapter 1. So hopefully we can cover section 5, 6, 7, 8, because it's all about differentiability, differentiation, right? So I mentioned earlier this course. So maybe let me make this roadmap. So roadmap for this is a function. Right? We start with function. Right? We talk about the polynomial functions, rational functions, exponential functions, logarithm functions. Yeah. So from function, we talk about limit. But this textbook is trying to go around limit because many people have a lot of confusions about how to understand the limit. Then in limits, we talk about something called differential quotient, right? F of x plus h minus f of x divided by h. So basically, this is the slope of 2 points. Right? One point is x plus h, comma, f of x plus h. Another one is x, comma, f of x. So the slope of those 2 points. But then we use the limit idea. We said, okay, let such h approach to 0. So basically, we have 2 points. Right? We have x plus h, f of x plus h has 1 point, and then x, f of x as another point. So what does this notation mean? This notation means let's push h to be 0, as close to 0 as possible. So then these 2 points becomes 1 point, right? Imagine we'll have this. Let's say this will have such function, right? Then we'll have this line. We'll have this point, we'll have this point. Maybe this is x, f of x. This is x plus h, f of x plus h. So what do we do? And this is saying, let's push this point, which is x plus h, f of x plus h. We push this point to x, f of x. So then what happened? So you see this one is called, actually, let me draw a better graph. Let's draw a graph like this. Okay. Let's say I have these 2 points. Use these 2 points. So I want to push this point, keep going, then to this one. So what happens? This is secant line. So this line cuts through the parabola by 2 points called a secant line. Once I push this point to be this point, it becomes the tangent line, right? So this is still part of the graph. It becomes a tangent line. So then what do we name this? We give the definition derivative of this function. That's how we define this function, this differential quotient formula to be derivative. So that's a differentiation. Or derivative of a function, right? Differentiation. So how we define the derivatives of a function, that's it. That's this one. We use the differential quotient combined with the idea of limit. The graph is this one. We had 2 points to start with. We push 1 point to the other point. So it becomes the value at the 1 point. So that becomes the slope of the tangent line, right? For line, we can always write it as mx plus b. Now, what's the derivative? The derivative is just such slope. So that's the connection. We're going from function to limit to differentiation. Then we're going to end with something called an integral, right? Integration. Integration basically is upset of differentiation. So it's called anti-differentiation. So then we see how do we use those ideas in life applications. So that's the roadmap of this course. Okay, so 1.5 talk about 2 things. Differentiability, just can this function be differentiable? You know, can you apply differentiation for such a function? So that's called a differentiability. And the continuity. But I like to talk about continuity first. Okay. So let's see these graphs. So it's easy to see from the graph. So if the graph is one piece of string, just imagine, right? You see all the four graphs, we can imagine as one piece of string, right? If we use our hand to take this from this point, right? So this is just one piece of string. There's no break, right? Same thing here, same thing here, same thing here. So that's from the graph point of view. Then let's see some discontinuous functions. This is still continuous. These are discontinuous, right? Right, if we take this one, you see this is one piece. This is another piece. This is another piece. We have three pieces of strings for this function. This is called a step function. And then this one, same thing. So at this point, x equals 2, use the string breaks, right? We have two pieces of strings. Same thing here. Right? This string breaks into three pieces. Right? So it's easy to detect from the graph of a function, but it's not easy to detect from the expression, the algebraic expression of a function. But normally, let's see rational function, right? Let's say we have 1 over x as a function. So x cannot be 0, right? So the graph looks like this. One piece of string here, one piece of string here. So two pieces of strings. So because x can never be 0. So that's about the continuity. Right? Then what's differentiability? So we know that a lot of things. So what's differentiability? Differentiability means picture-wise means smooth. Right? It means smooth. Let's talk about picture-wise. You see here, this point. Oops. This is a sharp point, right? This point is a sharp point. We call vertex. And this point we call cusp, right? So at those points, not differentiable. What's wrong? Why is not differentiable? Remember, differentiability in graph-wise, right, means the slope of the tangent line. Slope, so f prime of such, so this is a red piece is a function. The blue piece is a tangent line, right? So f prime derivative of the function at such point of x equals to the slope of this blue line. Right? So, okay, so that's the definition, right? So let's see what happens in this point. In this point, right, I have two tangent lines. At this point, I can extend this line, right? And I can extend this line. So I have two tangent lines. So which one I should follow? It's not unique, right? So we cannot define. Same thing for this. If I go this way, I can draw the tangent line like this. If I go with the left graph, I can draw a tangent line like this. So I have two tangent lines at those kind of points. So those points are not differentiable. Same thing for those two. Okay. Similar. At this point, you see, I can extend this one, right, as a tangent line, and I can go from this one as a tangent line. I can draw two tangent lines. Same thing here. Why this one? This one is a little bit different. What is the equation of this line? The equation is x equals to 8. What's wrong with x equals 8? X equals 8 is not a function. It's an equation, but it's not a function. Right? Horizontal lines are functions, constant functions, but vertical lines are not a function. Why is not a function? Because a function, if I have one set of something, another set of something, the function go between of them. Maybe I have 1 and I have 2. 1 goes to 3, 2 goes to 3 is okay. But I cannot do 1 goes to 3, also 1 goes to 2. That's not a function. Let's see what happens here. You see x equals to a here, goes 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 here. Right? You can think as one person cannot have 2 ages, right? So this is a people's name. This is age. You cannot, anybody cannot have 2 ages, right? Either you're 3 years old or you're 2 years old. But here what happens? You see A being sent to so many places, right? So one x value goes to all the values of y. So a person has many ages. That's not a function. That's just by definition. Okay, so in these kind of cases, right, functions are not differentiable at such points. All right, so this back again to the live application, saying, okay, a railroad company charges $10 per mile. This is the rate of change, $10 per 1 mile, right? If it's X mile, that would be 10X, right? That's how much they charge. To haul a boxcar up to 200 miles and $8 per mile for each mile exceeding 200. In addition, the railroad charges 1,000 handling charge, right? Constant, that's a one-time charge per boxcar. So graph the cost of sending a boxcar X miles. All right, so how do we graph this? If X at the most 200 miles, so that give us like a domain range, right? So X can only go up to 200 miles. For the first domain, we separate the domain into 2 parts by the context, right? Let's see if I can show the context at the same time, show the question at the same time. So up to 200 miles, that's how they charge, right? $10 per mile. If it's greater than, so this is for X less than or equal to 200. So AX, if X is greater than 200. So this is 10X. So that's why we have to make a piecewise function, right? Because the domain being separated into 2 parts. So X can be less than 200 or X can be greater than 200. If X is less than 200, it charges $10 per boxcar. If it's greater than 200, it charges $8 per boxcar. And the one-time charge for less than 200 is 1,000. For more than 200 is 1,400. This is just one-time handling charge. So we make these functions, piecewise functions. Then now we can graph, because each one is a linear. We need 2 points, maybe the point to be a checkpoint to graph it. So here we have this graph, right? So less than or equal to 200 is this line, straight line, linear function. If it's greater than 200, is this line. The slope is a little smaller, right? Comparing A to 10. So that's the graph of that. So example 2 is similar, all right? Continuity, the definition is this. So how do we, picture-wise is one piece of string. But from the expression point of view, we express like this. So the limit of x, when x approaches a, equals to the function value. What does it mean? Remember limit, let's say I have function graph looks like this. Oh, I should, you know what? I should erase some. Oops, erase the whole thing. So I should make a graph maybe this way. I'm just making this up, okay? Let's see, this is a such function, piecewise function. So the function is not continuous, right? It's not continuous. And the limit, let's see what happens. At every point here, the solid dot, we have this. We have this, so this equation holds. The limit from left of A, limit from right of A equals to the function value. But what happens, let's see, this is -1 here. What happens when x approaches -1? The function value, let's see, this is 2. The function value equals 2, right? Equal to 2 from the left-hand side. Remember, left-hand side is negative. From the right-hand side, it looks like a half. So one side is a half, one side is 2. They're not equal to each other. Left-hand side limit, left limit, not equal to right limit. So of course, does not equal to, only the right limit equals the function value, but the left limit, the right limit does not equal to function value. Only the left limit equals the function value. So the limit does not exist. And the function is not continuous at x equal -1. Same thing for this point. X is not continuous. So from graph is easy to see, from expression, from the equation. So when it's not continuous, so those two are not equal to each other. Let's see these ones. So this one, limit exists, because limit equals to 2. But there's no such function value, right? You see y f of, this is a 3. F of 3 does not exist because it's an empty circle. So the equation does not, so the limit equation and the function equation are not equal to each other. X approaches a, f of x. So this equation does not hold. But this one, of course, left limit. So this is left limit. This is right limit. Left limit is 1. Right limit is 2. Of course, they're not equal to each other. The function value is 2. So this equation does not hold. Well, this one from the left-hand side of 3 goes to positive infinity. From the right-hand side also goes to positive infinity. But infinity is a concept. It's not a number. If limit exists, it's a real number. So the limit also does not exist. The function is not continuous. This one is the same as the first one. All right, so those two are in the same situation. All right, that's section 5. Talk about continuity, talk about differentiability. Let's see some rules about differentiation. So now we're back to this notation. Okay, so this notation is the same as f prime of x. So this basically is saying if we have a scalar, a number multiplied by a function, and this number we can pull out. What does that mean? Let's see, we have x squared, right? We know how to differentiate x squared. When we differentiate, we put 2 down, and then we subtract 1 from the exponent. So we have 2x raised by 1. Basically, we write as 2x. But now, what if we have 2x, let's say 3x squared? 3x squared. So what we can do is we can leave this 3 outside of the differentiation. We can leave the 3 outside to differentiate this. Then in the end, we multiply. So that's the first one. So we can pull the constant out. And if we have two functions adding together, we can differentiate each one. So what does that mean? That means if I have 2x squared plus 3x, right? If I want to differentiate this, I can differentiate separately. I can differentiate 2x squared, and then I differentiate 3x. And with 2x squared, I can put 2 outside to differentiate x squared. 3, same thing, I can differentiate x, right? So x squared, I differentiate, I get 2x. Differentiate x, I get 1. Then I get 4x plus 3. So the second root, right, plus the first root. So the last one is saying, if we have a function raised by an exponent, right? So what do? So we have to do, so they call this the power rule. Basically, we call this a chain rule. So we'll talk about later on too. So what happens here? So first we have to pull this exponent outside, right? Let me give you an example. It's easier to understand. So let's say I have x squared plus 1 raised by 3, right? So this is my function. I want to use power rule to differentiate this. So what do? I could just follow number 3. I pull this 3 out. Now I keep the inside. Remember the inside is g of x, right? This inside is g of x. Then I subtract 1 from the exponent. Then I differentiate the inside. So this is our g of x. This is r. Then I simplify this. Right? I get 3x squared plus 1. 3 minus 1 squared. Then multiply by, I differentiate x squared plus 1. Well, x squared is 2x. Well, derivative of 1 is 0 because 1 is a constant. So then I can multiply 3 with 2x. I get 6x times x squared plus 1 squared. All right. So this is one of the applications of chain rule by applying chain rule, which means we have to multiply, we have to differentiate the function twice, 2 layers, not twice. Right? We have to differentiate the outside, then differentiate inside. What do I mean by outside and inside? You see this, or we can understand as compositional functions, right? The inside is a function, g of x. Then raised by 3 is another function. So this is a compositional functions. So we need to apply chain rule. So let's see some more examples. So let's see this one. I can pull these 2 outside. I just differentiate x raised by 5. So how do I differentiate x raised by 5? By power rule. I pull 5 down, then I subtract 1 from the exponent. So 2 times 5 is 10. 5 minus 1, that's 4. And this one, you see this is x cubed divided by 4, that's 1/4, right? I can pull this 1/4 outside. I can differentiate x cubed. Or that's 1/4 times 3x squared. So which I get 3/4x squared. This I have -3. I can pull outside -3. Then I just differentiate 1/x. Right, 1/x I can write as x raised by -1. Then I differentiate. So -1 I put down here. Then I minus 1 from the exponent. So -3 times -1, that's +3. -1 that's -2. So I can rewrite as 3/x squared. Why? Because x raised by -2 is 1/x squared. Then I multiply by 3, right? I multiply by 3. So this one, I can pull the 5 outside, differentiate square root of x. And square root of x, I can write as x raised by half, right? Then when I differentiate, I get a half x raised by half minus 1. Well, half times 5, that's 5 over 2. Half minus 1, that's x raised by negative half. So what is a negative half? Negative 1 means I go to the denominator, x raised by half is square root of 2, right? So we get a 5 divided by 2 times square root of x. Okay, let's see this one's sum rule. So this one, I can differentiate each one separately, right? But now we know a little better, so let's differentiate faster. So the first one, I can differentiate as 3x squared. The second one, just 5. So this one is 4x raised by 3, then minus, right? Let's differentiate 3 over x squared, right? Let's pull 3 outside. Then we want to differentiate x raised by negative 2. How do we do that? We get negative 2, x raised by negative 2 minus 1, negative 3. Then I have 3 times negative 2, negative 6. Then x raised by negative 3 is 1 over x cubed. So I can rewrite as negative 6 divided by x cubed. So 4 raised by x cubed minus negative becomes plus 6 divided by x cubed. Well, this one C, I can write as 2 times 7, 14, x raised by 6 minus 5, x raised by 4, plus 0. I don't really have to write it because derivative of a number is a 0. Let's see this one. Let's see the practice. So this example. Okay, let's go through this example. So they call general power rule, but it's one of the chain rule. All right. So let's say we have to take a derivative of this. So first, we want to deal with the outside layer of square. Right? Remember that's R. So we put 2 up front. We write whatever the inside is. We don't change the inside yet. Whatever the inside is. Then with 2 minus 1, get this 1. Then we differentiate the inside. Right? We differentiate inside, we get 3x squared. So then we simplify. You see, this is 2 layers, right? We have to differentiate the outside layer, then we have to differentiate the inside layer. So you cannot do 2 steps into 1, okay? I see students often make the mistake. Do 2 steps into 1. No, there's 2 steps. Do not combine into 1. The first step is you differentiate the exponent, right? So we put 2 down here. We subtract 1 from 2. 2 minus 1 is 1. The inside, you see, does not change. We keep the inside for the first layer. Then we differentiate the inside. Okay, so 2 layers. Okay, do not combine the 2 steps. Okay, let's see this example. So this will have 2 layers. So first, we want to rewrite this one as 1 minus x squared raised by half. You see, we have 2 layers now, right? So when we take a derivative, we consider the first layer. We're going to deal with this first. So the derivative will be half times whatever the base is, then half minus 1, first layer. Then the second layer is we have to deal with the inside. We have to take a derivative of this. Well, what is the derivative of that? Derivative of 1 is 0. Derivative of negative x squared is negative 2x. Now we do half multiplied by negative 2, we get negative 1x. Then we just simplify this by x squared. Then half minus 1, negative half. We simplify this, we get a 1, the negative x in the numerator, because x does not have a negative exponent. Only this term raised by negative half, so that's the square root of 1 minus x squared. Okay, so what did I do? I deal with the first layer, I take a derivative of a half, right? So I pull half down and minus 1 from a half. I keep the base, right? This is the base. I just deal with the exponent, I keep the base. But then I multiply the derivative of the base. So 2 steps. Then I simplify, all right? Let's see this one. So this one I can rewrite as x cubed plus 4x raised by negative 1. Again, I'm going to deal with the exponent first. So when I take a derivative, I can write it as y prime. That equals negative 1 times whatever the base is. Then I subtract 1 from negative 1, minus 1, minus 1, I get a minus 2. Then I multiply the derivative of the base of the inside, which is 3x squared plus 4. Then I simplify, right? This term is raised by negative 2. That goes to the denominator. And this term raised by 1. That goes to the numerator. So this one is similar. Right? I can write it as a 5 times 1 plus x cubed raised by 1/3 because the index is 3. So I can write as a 1 over 3. Then when I take a derivative, I can leave 5 outside, right? Then I pull 1/3 down. I keep 1 plus x cubed. Then 1/3 minus 1, negative 2 over 3. Then I multiply by the derivative of the inside, which is 3x squared. Right. Then what do? I have 1/3. I have 1/3 here, multiply by 3, that becomes 1. Then multiply by 5. I still have 5 here. Right. Then I have x squared in the numerator. So this term is raised by negative, that goes down the denominator. Okay, that's a cubic root. So this denominator in the exponent is 3, and 1 plus x cubed being squared, right? So fractional exponent. The top means power. The denominator means index. So those guys called the index. All right. There's some rules for when we differentiate, right? We don't have to go through the difference quotient, which we could, but we do have this rule of thumb to do faster. Let's see some more derivatives. Right, let's see this one. Just different notations, right? ds, dp, think as df, dx, okay? Just different letters, but the meaning is the same. So we want to differentiate this. So what do? We can write as s prime. You see this is defined as s. We can write as s prime equals to 3 times 10, that's 30. Right, then p squared plus 5p plus 1. Now 10 minus 1, 9. Then multiply by the derivative of inside, which is 2p plus 5. And that's it. We don't have to simplify for this. Right. Let's see this one. Oh, be careful with this. This is dp, only one variable. Now we have different variables. We see here we have a, we have t, we have s. So what's important is this. Look at this, dt. So this is, so t is a variable. A and s we treat it as numbers, right? So dt, we only consider rate of change of this in terms of t. So s squared with us is constant, right? So what do we do? So we have 2at, we're treating a as a number. So t squared, derivative is 2t, so a times 2t, 2at. Then minus this, st raised by minus 1, that's s divided by t squared, right? Remember we have x raised by -1. That's s as a number. Then this one is 0. So that's it. The derivative is this. So the derivative is in terms of t. The rate of change only consider t. Of course, we can do second derivative, right? The first derivative, a lot of times, is a function. And we can keep taking derivatives. Let's see the first one. Actually, let's see b first, because b is easier, right? So the first derivative, oops, what I'm doing. So the first level of derivative, we just call f prime of x. That's just equal to 2, right? Then we differentiate this. We're treating this as a function. We differentiate this. So we call f double prime. We make one more apostrophe. What is it? 0, isn't it? Because derivative of constant is 0. Now let's try the first one. So the first derivative f prime equals to 3x squared, right, minus 1 over x squared. Then the second derivative, which means we take a derivative of this first one, which is 6x, right, 3 times 2, 6. Then 2 minus 1 is x raised by 1. Then plus, well, what is the derivative of 1 over x squared? That's x raised by -2. That's a -2, x raised by -3, right? Negative times negative plus. So that's plus 2 over x cubed. Let's see C. So the first derivative is, in terms of t, is a half of t raised by -1/2 minus half t raised by -1/2 minus 1 minus 3/2. So we simplify this, we write as 1 over 2 square root of t, right? T raised by half is square root of t, but this is negative. Then minus 1 over 2 t square root of t, right? Because t raised by -3/2 is 1 over t raised by 3/2. That's 1 over t raised by 3 square root, right? So we can take t out to be t square root of t. So those are different notations for derivatives, right? We see f prime of x can be written as a df of x dx. Sometimes you see like this kind of notation, df dx of x, right? Y prime we can write as dy dx. Y double prime second derivative can be written as d square f dx square x. So why is that? Because the first linear we can write as d dx, right? Or df, we can write like this. Then we want to take a derivative of this, we can write another layer because this is a function, right? Now you see we have d square dx squared f of x. So that's how we got this notation. So similarly for this one. Let's see this example. We're given y equals to this polynomial degree 4, and we want to find the second derivative. Then we want to evaluate x equals 3. Well, better think this way as f of x, right? And we want to find f double prime of 3. That's the goal. So we need to find the first derivative. So we'll take a derivative. So we'll get a 4x cubed minus a 15x squared. And that's it. Then we take a derivative of this first derivative. We have 12x squared minus 30x. Then we want to evaluate when x equals 3. So 12 times 3 squared, 9, minus 30 times 3. Well, 12 times 9, 108, right? Minus 90, so we get 18, right? So the notation looks annoying, but that's what it means. That's what this function wants. It wants you to take a second derivative, then evaluate at x equals to 3. So this one is similar. I'm not going to do that. So the derivative as a rate of change. Derivative, okay, the change of the slope of this tangent line. Okay, I'm going to skip that. Okay, let's see this. 1.8. Right. So what is this? F of b minus f of a divided by b minus a. Slope, right, of 2 points. One point is a f of a, another point is b f of b. So average rate of change. So f of x equals x squared, we can calculate in between of, so for x in between 1 or 2, in between 1 and 1.1, 1 and 1.01. So you see the x value gets closer and closer to 1. So this helps us to understand, the secant line I drew earlier, right? We had 2 points. We had 2 points, right? Of the 2 points, we can draw a secant line. Then we can push 1 point to the other point. Then we get this tangent line. So you see the x value gets closer and closer to 1. So we will see the trend, how this point being pushed, push. That's how the secant line becomes a tangent line in the end. The differential quotient I explained earlier. And then we call this instantaneous rate of change, right? Because imagine this. Imagine this is a business model. This is a certain month. This is a certain month. This is another certain month. We want to find out in between of these 2 months, what is the average increase? What sometimes decrease? What's the average change, right? In business, it could be increasing or could be decreasing. So usually we have to find the 2 points, right? We use 2 points. We do, f of b minus f of a divided by b minus a. That's called the average rate of change, right? Because we average out all this. But now we can do precisely at 1 point. Because the idea of the limit, that's the marvelous thing about limit. We push the edge to be 0. We push this point to be at this point. And we can find exactly the instantaneous rate of change at the very moment, right? We want to find out a business, how is the business increasing or decreasing? at a certain date, at one date. You can imagine like that. So that's the beautiful thing about this miracle of this concept of limits. Okay, so mainly this chapter is about the derivatives, right? Taking derivatives. So next class, we'll talk about how to use these derivatives ideas in live applications. If you have any questions, you can ask me in email or in the Discord group, all right?